move a distance s. Then the work done is given by work is equals to F cos theta times s. So basically, this is the general equation for work. So the reason why we are giving this equation here is that mechanical energy often involves work. Because when we talk about mechanical energy, it often involves the work done on the system and the work done by that system. So this is a diagram of this what we're trying to explain here. So if your force is parallel to the surface through which is acts, so you don't need of, then that means that theta is 0. So that means that will be ordinarily F times S. But if the theta is not 0, then the work is F cos theta times S. So as you can see, this is generally how it works. This is the basics and fundamental of work. Now we also have two other types of work. We have work which is related to mechanical energy, and that is potential energy and kinetic energy. Now if you have been able to watch the SS1 course of this channel, you will know that potential energy is the energy possessed by a body by virtue of its position or state of configuration, whereby kinetic energy is the energy or capacity to do work based on the motion of an object. So they are two different things, but they are still made up of mechanical work. Our study of mechanical energy will not be complete without considering the conservation of mechanical energy. Now, conservation of mechanical energy, in the previous episode we talked about the conservation of momentum. So basically, from that knowledge you can still understand this one as basically the fact where in a closed or isolated system the total mechanical energy is always conserved, or it is constant, although energy may change from one form to another. So basically what this means is that when we have a closed mechanical system, energy does not move in and out of that system, but that energy can be transferred from one form to another, because there are different forms of mechanical energy. We have electrical, we have potential or kinetic energy, and electrical energy can also be converted to mechanical energy and vice versa. So there are different conversions that can occur, but the most important thing is that each of these conversions does not alter the energy content of that closed or isolated system. We as human beings, as intelligent as we are, we have been able to come up with various setup and arrangements that can help us do work, and these are known as machines. Now a machine is defined as a device or tool which allows a force or effort applied at one point to overcome a resisting force or load at another point. Now machines work on the principle on natural principles. For example, what goes up must come down, which is the principle of gravitation. So basically when we study this principle and we understand them, we can be able to set up different systems that can perform work by making use of these machines. So these machines are basically set up that help us to do work easier, faster and better. Let's break down some concepts and terminologies in mechanical energy, and one of these is mechanical advantage or force ratio. Now the effort is the force applied to a machine and the load is the force or resistance overcome by the machine. The ability of a machine to overcome a large load through a small effort is known as its mechanical advantage ratio, and this is given by the load divided by the effort. Another way of referring to mechanical advantage is seeing it as the ratio of the output to the input force. So basically, it's the work done by the system divided by the um, work supplied to the system. Another terminology which we will deal with here is the velocity ratio, which is the ratio of the distance moved by the effort and load in the same time interval. So basically, it's distance moved by effort divided by distance moved by load. So this velocity ratio is rightly defined because it represents the velocity of the effort and the velocity of the ratio between them. So the more the velocity ratio, the more the amount of useful work that will be done. Next, let's talk about efficiency. Now, the efficiency of a machine is defined as the ratio of the useful work done to the work put into the machine. So the efficiency of a machine is expressed as a percentage, that is useful work done to work put into the machine times 100%. Now, because work is equal to force times distance, we can say that let's say that is equal to the load over effort times the distance over load over distance over effort times 100%. So this is another way of expressing the efficiency, and that would be on the numerator. You can say that we have the load times distance over load, and that constitutes the work done by the load. work done on the load. Then on the denominator we have the effort times the distance over effort, which is the work done by the effort. So at the end of the day, we have this as the mechanical advantage over velocity ratio, because this is the inverse of the velocity ratio multiplying the mechanical advantage. So this is another way of expressing the efficiency, which is as mechanical advantage divided by the velocity ratio multiplied by 100%. There are different types of machines which we can deal with or consider. The first is the lever, which is one of the simplest machine known. It is one of the oldest machine too, and which we can also overcome a large resistance by the application of a small force with a lever. So all you need is a lever, and then when you apply a small force, you have a large force, which is the load being moved or worked on. Now we have different types of levers, and these are also known as the classes of levers. For example, we have the first order, second order, and third order of lever. In the first order of lever, the fulcrum or pivot is the load and the effort. So examples of these are the crowbar, a pair of scissors or pincers, a claw hammer, and plier. These are instruments that work based on the principle of force lever, and one common thing about them is that they have their fulcrum at the middle of the load and the effort. So the velocity ratio is usually greater than 1, but it could be less than or equal to 1. So here are examples of the first class lever. You can see this is a pair of scissors, this is a crowbar. Then we also have the claw hammer, which is another example, and then a plier. The second class of lever, which we'll be talking about here, is called the second order of lever, and in this case the load is between the effort and the fulcrum. So examples of this class of levers are wheelbarrows and nutcrackers. So the mechanical advantage and the velocity ratio are always greater than 1 in this case. The third class of lever, also known as the third order of lever, is a kind of lever in which you have the effort between the load and the fulcrum. So examples of these ones are forceps, tongs, forearms, and so on and so forth. So these are the examples. You can see this forearm. So in the middle you have your fulcrum, in the right you have your load, and then at the left you have the effort, which is the muscle that moves the lower arm. So this is an example of a third class lever. And in this case, the mechanical advantage and velocity are less than 1 in the third class lever. Another type of machine which we can talk about is the pulley, and this pulley is also forms a pulley system. We have different types of pulley system. We have the block and tackle and so on and so forth, but specifically we'll be dealing with the block and tackle here. Now this is one of the most widely used machine in and these pulleys, they are often used in the construction sites to raise or lower heavy loads. So it works on kind of like a very simple principle. All you need to do is drag the one end of the rope, and then you have your load working moving closer to you in the opposite direction. So if you drag the other end down, you have the load moving upwards and vice versa. So this is an example of a block and tackle system. You have 4 ropes. So basically, in a pulley system, the velocity ratio is generally equal to the number of pulleys. So in this first video, in this block and tackle system, we have four wheels. So on these wheels, they make up the pulleys. So basically, we have 4 pulleys. So that means our velocity ratio will be 4. If we had 5 pulleys, our velocity ratio would have been 5, and so on and so forth. Now let's address an example that deals with efficiency and machines. So in this example, we have that a machine has a velocity ratio of 5 and is 80% efficient. What effort will be needed to lift a load of 200 newtons with the aid of this machine? Now in this case, we are told that the velocity ratio is 5, and then we have the efficiency as 80%. We also have the load. All we need to look for is the effort. So we'll make use of the formula for efficiency, which is MA over VR times 100%. So here our MA, which is mechanical accuracy, is equals to mechanical advantage rather, is equals to 200 over effort. So let's keep that down. Then we also have our VR as 5. So we plug in into the equations. We have 200 over 5E times 100 equals 80. When we change the subject of the formula and make E the subject, we have E equals 200 times 100 divided by 80 times 5. So when we evaluate that, we'll get 50 newtons. So that means our effort is 50. We have another example of a machine. Now this is called an inclined plane. So in this example, you can see a man trying to push a barrel up a ladder, and this ladder is called an inclined plane. It forms an inclined plane because it is at an angle to the vertical floor, and this inclined plane helps us to reduce the work that would have been done if we were to raise this barrel through, if we were to raise it vertically up on the high floor of the lorry. So basically, this inclined plane help us do work as a machine. So we have different properties of an inclined plane. We have the formula for velocity ratio of an inclined plane, which is the inverse of the sine of the angle of elevation of the inclined plane, or the angle that the angle by which the inclined plane is elevated. So basically, this angle is to the horizontal, and the load is lifted through a vertical height. So the velocity ratio and the inclined plane, they are related to the trigonometric properties of that shape, which is a triangle. Friction along the plane also affects the efficiency, and the mechanical advantage will be less than the velocity ratio of an inclined plane. Now this is the equation representing the relationship between the velocity ratio and the sine of the angle of an inclined plane. So here the velocity ratio is equal to the distance moved by effort divided by the distance moved by load. So the distance moved by effort is basically the the um, the surface of the inclined plane, which through which the object moves. That's the distance moved by effort. But the distance moved by load is the vertical height through which the load is raised. So that means that if you look at it from a trigonometric standpoint, that is the inverse of the sine of the angle of the inclined plane. Here's an example that will help us to understand this concept better. So here we have the floor of a lorry is 2 meters high. A plank 5 meters long is used in an inclined plane to raise some load up the lorry. If the efficiency of this machine is 50%, what is the minimum effort required to raise 200 newtons up the plane? So here we are still going to make use of the formula for efficiency, which is MA over VR times 100%. All we need to do is plug in the value for the mechanical advantage and velocity ratio. That's velocity ratio is the inverse of the sine. That is 5 over 2. That's 2.5. Also, okay, we're looking for the effort. So when we plug that into our equation, we have our mechanical advantage equals 50 times 2.5 divided by 100. That's 1.25. So when we equate that to the formula for mechanical advantage, which is load over effort, then 1.25 equals to load over effort. That's equals to 200 over effort. When we change the summation of the formula, we have 200 over 1.25 equals 160. So that is the effort that is used to raise the load. The fourth type of we're dealing with is the wedge. Now the wedge is a combination of two inclined planes. It is used to separate bodies which are held together by large forces, like is used for splitting things like timber. Example of wedge type of machines are axes, chisels, knives, and other cutting tools. So basically, they have the sharp edge, and are used to cut through substance. So they apply the principle of pressure, which says that pressure is directly proportional to force and inversely proportional to area. So basically, when you want to increase the pressure of a on a substance, all you need to do is you need to decrease the area. So that's why these substances, the sharper the edge of the wedge, the more pressure you can apply, and as a result, the more effect you can when you want to cut things into pieces. So that's why a knife has sharp edge, and all these substances all have this edges that looks like wedges. The fifth type of machine we'll be talking about here is a screw, also known as a screw jack. Now the screw can be considered as an inclined plane wrapped around a cylinder. So that's how it looks, and the hypotenuse of the inclined plane forming a spiral that constitutes the screw thread. Now basically the difference between between the height traveled by the screw when it performs one revolution is called the pitch, and then you have different terminologies used to understand the motion of screws. For example, the velocity ratio is the ratio of the circumference of the screw to the pitch. That is the velocity ratio. And also the mechanical accuracy, rather the mechanical advantage, is also the ratio of the circumference of the screw to the pitch of the screw. So a screw is basically used in when we make use of that that it's called a machine. That machine that is used to raise a car up. A screw jack is called a screw jack. It's used to lift large loads such as a motor car. It consists of a long vertical screw which threads into a heavy base and a long rod called a tummy bar. Now this screw jack, when it does work by converting circular motion into linear motion, and that is an example of how screws work. The fifth machine which we will talk about in this video is the wheel and the axle, and it's a machine that is used to lift water from deep wells. It's used to raise heavy loads such as the anchor of ships, and it is illustrated in this diagram. You can see this wheel and axle, and how it works. It consists of a round cylindrical drum, round which a long rope is wound, leaving a front end where the effort is to be applied. So the wheel has a large radius. Attached to this wheel is another cylinder, the axle, having a common axis with the wheel but of radius r, which is less than that of the wheel. So you can see there are two wheels, one of a large radius and one of a small radius. So the velocity radius is just gotten. The velocity ratio is gotten by the distance moved by effort divided by the distance moved by load, and it is equal to the radius of the large wheel divided by the radius of the smaller wheel. That is the velocity ratio. And in most cases, in the absence of friction and in an ideal environment, the mechanical advantage is also equal to the ratio of the large radius to the smaller radius. So that is how it works, and that is equal to the radius of the wheel divided by the radius of the axle. So you can see this wheel and axle in machines that are used to lift loads and lift water from wells. Finally, the last type of machine we'll be dealing with here are the gear wheels. Now these gears, they are commonly used in cars, bicycles and cranes. In this machine, the principle of the wheel and axle is applied to two wheels, called two wheels of different load height, connected by a belt and rotating on a separate shaft. Now you can see this is how a gear wheel looks like, and here both the load and effort are applied to the shaft, and the velocity ratio is given by the number of teeth on the driven wheel divided by the number of teeth on the driving wheel. So it is the number of teeth on driven divided by the number of teeth on driver. So basically that's the velocity ratio, and a gear is very common in many machines like our cars. Or the car you use to enter to transport yourself from one place to another, most components that help the car to propel itself contain gears, like the engines and the transmission. So gears are considered machines, not just gears. They are very important, and they have become integrated in our everyday world. Now I thank you all for staying with me through this video, and at the end of this video now I'm giving you a question for you to solve. You can also post the answers as a comment, or you can send the answers to the WhatsApp number in the description of this video. Thank you for watching, and I hope to see you next episode.